Controlling the materials which are needed to fuel nuclear weapons has been a topic of arms control deliberation since the end of World War II. The debate has continued for 5 decades. The breakup of the Soviet Union in the early 1990s has opened up new opportunities to reverse the nuclear arms race and has led to a renewed emphasis on limiting the spread of nuclear weapons. In his 1992 Non-Proliferation Initiative, President Bush stated that the United States would no longer produce plutonium or highly enriched uranium for nuclear explosive purposes, and called for countries in regions of tension, such as the Middle East and South Asia, to take similar action. And in 1993, President Clinton further focused U.S. non-proliferation policy.
We will pursue new steps to control the materials for nuclear weapons. Growing global stockpiles of plutonium and highly enriched uranium are raising the danger of nuclear terrorism for all nations. We will press for an international agreement that would ban production of these materials for weapons forever.
Plutonium is generated when the uranium within reactor fuel absorbs neutrons as the reactor operates. During this nuclear reaction, plutonium and highly radioactive fission products are created. The amount of plutonium generated in the fuel depends on the reactor power level and how long the reactor operates. Plutonium is recovered by chemically separating it from the remaining uranium and the fission products at reprocessing plants. One site of past U.S. weapons material production is the 1,450 square kilometer Hanford site, located in southeastern Washington state. It was known as the Hanford Engineer Works during World War II. Hanford's first reactor, B, was the world's first full-scale nuclear facility. It was built for the Army Corps of Engineers and the DuPont Corporation in just 11 months between October 1943 and September 1944, and is now listed on the National Register of Historic Places. B reactor, in conjunction with the world's first chemical reprocessing facility known as T plant, produced the plutonium used in the first atomic bomb, tested in the desert of New Mexico in July of 1945. Throughout the years, the Hanford site continued to be the United States' major plutonium producer. Nearly 2/3 of the United States' total plutonium output came from Hanford during the production era between 1944 and 1989. The Savannah River site in South Carolina produced the rest. Following World War II, U.S.-Soviet nuclear arms competition began, and for the next 2 decades this race dramatically increased. In order to meet the nation's demand for nuclear weapons material, 8 additional reactors were built on the Hanford site. The first 7 reactors were similar to B reactor in most features. D, F, H, DR, C, K East, and K West were built between 1943 and 1955. They were moderated by graphite and cooled by water taken from the Columbia River. Like B reactor, these were known as single-pass reactors because the water used for cooling was taken from the river, treated, passed through the reactor only once, and then sent to holding basins and ultimately returned to the river. The Hanford site's final production reactor, N, began operations in 1964. It was not single-pass. It still drew water from the Columbia River, but recirculated its primary coolant. It was also graphite moderated, and not only produced plutonium, but provided steam for electrical power production. Several chemical reprocessing plants were built: T plant, B plant, U plant, redox, and Purex. These enormous plants ranged in size from nearly 150 meters to over 300 meters in length. They were built between 1943 and 1955. Purex was the last of these facilities to operate. The entire plutonium production process, from fuel fabrication, irradiation of fuel in the reactors, chemical processing of the fuel to extract the plutonium, and creation of the final plutonium product, was performed on the Hanford site. Throughout the years, the reactor fuel fabrication process went through a number of evolutions. This was primarily due to the fact that reactor technology was in its infancy, and everything associated with it was on the leading edge of science. Two types of reactor fuel were produced in Hanford's 300 area, single-pass and in-reactor fuel. Fuel fabrication process changes continued throughout the 1950s and early 1960s, as new fuel designs were implemented in attempts to solve fuel element failure problems, which plagued the single-pass reactors as they were operated at ever higher power levels in order to increase plutonium production. Some of the new designs included cored fuel elements, which provided a hollow inner space for the uranium to expand into during irradiation. Internally and externally cooled elements, which had a tubular hole down the middle, allowing cooling water to run both around and through them in the reactors. And projection fuel elements, which had small fins protruding from their sides to support the fuel in the various types of reactor process tubes. Fuel element fabrication activities for the single-pass reactors ended in 1971, when the last of these reactors closed. However, the fuel fabrication facilities continue to support many functions associated with the fabrication of in-reactor fuel. The fuel-making process for in-reactor was very different from that of the single-pass reactor fuel. The final design adopted was a co-extruded tube-in-tube fuel element. As with the single-pass reactor fuel, the co-extrusion process was carried out with various pieces of equipment, but the most prominent and unique of these was a Lowy press. It simultaneously pressed all of the fuel components, including the uranium core and all of the cladding components, to extrude a single fuel element. The co-extrusion process provided a more uniform bond between core and jacket than had been possible with older fuel fabrication methods. This improved cooling and eliminated hot spots, a cause of fuel failure. The in-reactor fuel elements had a tube-in-tube configuration with a coolant channel running down the entire length of the element. When completed, each element was 66 centimeters long and weighed approximately 24 kilograms. This was significantly larger than the typical single-pass fuel element, which was only 20 centimeters long and weighed less than 4 kilograms. The co-extrusion process was carried out continuously from 1960 until December 1986, reaching a peak of approximately 250 finished fuel elements per week in the mid-1980s. The Hanford reactors powered with this fuel were themselves engineering and scientific firsts. Reactors of the size and type constructed at Hanford required large amounts of water to cool the reactor fuel during operations. For single-pass reactors, raw water was pumped from the Columbia River and chemically treated prior to use in the reactors. Once in the reactors, the water was passed directly through long process channels in the reactor core, where the reactor fuel sustained the nuclear chain reaction. From there, the water flowed out the back of the reactors and was held for a few hours in retention basins to allow short-term radioactive impurities to decay, and then it was returned to the Columbia River. The core of these reactors was a series of interlocking graphite blocks. The graphite served as the moderator, slowing the neutrons from the fissioning uranium fuel in order to sustain the nuclear chain reaction. Aluminum process channels penetrated the graphite stack from front to rear. Each process channel held 32 fuel elements. The graphite core with its thermal and concrete shields formed the reactor block, which measured approximately 12 meters per side. Each block was enclosed in a welded steel box that functioned to confine a gas atmosphere composed of helium, selected because it would not react with the graphite and because of its heat removal capacity. Horizontal channels for control rods entered from the left side of the reactor, and vertical channels for safety rods entered from the top. The control rods were used to control and maintain reactor power. The safety rods were used to shut down the reactor in the event of an emergency. There were major differences between in-reactor and the older Hanford single-pass reactors. In-reactor recirculated its primary coolant and therefore released substantially less radioactive effluent to the environment. The primary coolant also circulated under pressure and at higher operating temperatures, which also allowed for power production. Another major difference was that N-reactor had a safety feature built into its design that would cause the reactor to shut down if a steam bubble or void were to develop in a process tube. In the single-pass reactors, a steam bubble or void would increase the reactivity, heightening the chances for a nuclear accident. Hanford's single-pass reactors were operated carefully and designed with multiple redundant sources of coolant to overcome this problem. They never experienced such an accident. The N-reactor building was a reinforced concrete structure on top of a thick slab of reinforced concrete. The reactor core itself was a cube approximately 12 meters on each side. It consisted of 1,650 metric tons of nuclear-grade graphite blocks, notched, interlaid, and penetrated by 1,004 fuel channels. Horizontal control rods entered the N-reactor core from both the left and right side. 108 safety channels passed through the core from top to bottom. To maintain safe and efficient reactor operation, the N-reactor core was surrounded by special layers of reflector graphite, then by water-cooled thermal shields constructed of boron steel and cast iron, and then surrounded again by a primary shield of high-density concrete. Helium gas formed the reactor atmosphere and helped cool the reactor. In preparation for fueling the reactor, fuel was placed in long monotube charges and then stored on wall racks beside the reactor work elevator platform. During the refueling or charge-discharge process, the charging machine picked up a set of monotubes from the wall racks and positioned them to be charged into specific process tubes. Once positioned, the charging machine ran the monotubes through the barrier wall and connected with the charge head adapter located on the process tube. High-pressure water was used to insert the new fuel into the process tube. As the new fuel was pushed in, it displaced the irradiated fuel out of the back of the reactor into the discharge chute. The discharged irradiated fuel, or spent fuel, was collected in underwater carts and then transferred to the spent fuel basin, where it cooled and was eventually packaged for shipment to storage basins. Over its years of operation, many changes took place at N-reactor. From 1965 to 1967, a co-product demonstration took place, in which tritium was produced in the reactor from special lithium aluminate fuel elements. Also, beginning in 1966, steam from N-reactor was harnessed to produce electricity for the domestic power needs of the Pacific Northwest. N-reactor was the only dual-purpose U.S. defense reactor. President Kennedy acknowledged this significant capability when he dedicated the reactor in 1963.
And I think it's very appropriate that we come here, where so much has been done to build the military strength of the United States, and to find a chance to strike a blow for peace, and to find a chance to strike a blow for a better life for our fellow citizens.
In January 1964, President Lyndon Johnson announced that due to a decreased need for special nuclear material, Hanford's single-pass reactors would be shut down in phase sequence beginning in December 1964. All 8 single-pass reactors at the Hanford site permanently closed by January 1971. N-reactor continued to operate to produce power, and in the 1980s it was again configured to produce weapons-grade plutonium. The accident at the Chernobyl nuclear plant in April 1986 brought worldwide attention to N-reactor because both were graphite-moderated reactors. Although the Chernobyl reactor was significantly different in design and did not have N-reactor safety features, N-reactor was placed in a stand-down condition for safety evaluation and design improvements. During this time, it was decided that plutonium generated from N-reactor was no longer needed for the United States stockpile, and the reactor never restarted. It was placed in cold standby by the Department of Energy in February 1988 and formally deactivated in September of 1991. Even after the shutdown of Hanford's 9 reactors, spent fuel from their operation still remained. The earliest spent fuel handling practice at the Hanford site was to keep the spent fuel in water-filled basins for a very short period of time, usually several hours to one day. The irradiated fuel elements then were loaded into shielded rail cast cars and taken to the 200 North area, where the fuel was stored for periods ranging from a few weeks up to 50 days to allow for further radioisotope decay before they were taken for chemical separation. In 1951, fuel shipments to the spent fuel storage buildings in the 200 North area stopped in order to reduce transportation costs and worker radiation exposure during fuel transfers. From that time, spent fuel at Hanford was allowed to decay while in the reactor basins. From 1964 to 1970, as each single-pass reactor closed, its spent fuel basin likewise closed, after all remaining fuel was sent to Purex for reprocessing. The N reactor continued to generate spent fuel as it remained operational through the 1970s and early 1980s to supply the Pacific Northwest with electrical power. This fuel remained in the reactor longer. Therefore, the resulting spent fuel contained plutonium unsuitable for nuclear weapons use. As a result, much of the fuel was not sent to Purex for reprocessing, and the N reactor fuel storage basin was not large enough to accommodate the growing inventory of spent fuel. The decision was made to use the K reactor spent fuel basins for additional storage. Today, the K basins hold the nation's largest single concentration of stored spent fuel. The existing fuel inventories include over 3,600 open canisters of spent fuel in the K East Basin and over 3,800 closed canisters of spent fuel in the K West Basin. This inventory totals approximately 2,100 metric tons of fuel. During plutonium production operations, the reactor basin's fuel inventory was shipped to the radiochemical processing plants to recover the plutonium from the spent fuel rods. The steps in this process generally included an initial fuel dissolving process that first removed the protective fuel cladding and then dissolved the now exposed fuel. Chemical separations processes were used to separate the plutonium from the fission products and then from the uranium. The plutonium was then recovered as a nitrate solution, which was converted to plutonium metal and used for weapons manufacturing. The earliest of these operations at the Hanford Engineer Works, using irradiated uranium or hot feed, began on December 26, 1944 at T Plant, the world's first full-size radiochemical processing plant. As with reactor technology, large-scale radiochemical processing operations were on the leading edge of science. Evolutionary changes in reprocessing technology resulted as new discoveries were made. These changes resulted in the sequential development of B and U plants, followed by redox and the Purex plant. B and U plants were built to provide additional reprocessing capacity. U plant never handled spent fuel, but served as a training facility and was later used to recover uranium from the waste generated by the other reprocessing plants. Each radiochemical processing facility was separated into two main portions, galleries and a canyon. The buildings were designed so that the control panel boards and chemical and service distribution were located in three galleries, one above the other along the front side of the building. The first gallery, at the basement level, was used principally for electrical distribution and control cabinets. The first floor gallery consisted of a piping loft containing steam, water, air, and chemical headers, as well as piping connections between the panel boards and weigh tanks on the second floor and through-wall cell piping. The second floor gallery was the control center for the cell equipment and was known as the operating gallery. The interior portion of the building below ground level, known as the canyon, contained a series of individual concrete cells having removable concrete cell block covers. The cell covers were constructed with overlapping stepwise edges to contain the radiation within the cells. As the Cold War and nuclear arms race continued, even higher production rates and more efficient spent fuel reprocessing operations were needed. Design for the Hanford site's reduction oxidation, or redox plant, began in 1947, with actual construction beginning in late 1949. The facility commenced operations with hot feed in January 1952. Like previous processing facilities, the redox plant operated most of the process remotely, using the gallery and canyon design concepts. Also, like B and T plants, redox began the process by dissolving first the fuel jacketing and then the solid uranium fuel core. Redox was unique in that it was the first radiochemical processing facility in the world to operate with a continuous or non-batch solvent extraction process. Early in 1950, national defense estimates showed that even with the increased production output from redox, there was still a gap between the capacity to produce plutonium and U.S. stockpile requirements. So in 1951, the development of a new separations process and plant was initiated, and design for the new separations processing facility began in July 1952. Construction began on the plutonium-uranium extraction facility, or Purex plant, in April 1953, and was essentially completed by April 1955. The design of Purex equipment and systems incorporated several unique new features. Among these, the most important to overall operations were the use of pulse columns rather than packed columns or mixer settlers to achieve actual chemical separation, and the development of liquid-liquid solid-type centrifuges. Other unique design features in the Purex plant included an irradiated fuel element storage basin, the first of its kind located within a separations facility. Also, a railroad tunnel designed to permit unloading of contaminated cast cars without compromising the ventilation system, and a soft wall at the east end of the building that consisted of concrete blocks and grout that could be removed for the installation of an additional crane or to enlarge the building at a future date. The plutonium nitrate solution produced by these Hanford reprocessing plants was originally shipped to Los Alamos, New Mexico, to be converted to metallic plutonium. However, since World War II, this process was seen as undesirable because of safety and security concerns. As a result, a process that would convert plutonium nitrate product to metallic plutonium at the Hanford site was needed. The plutonium finishing plant, or PFP, was placed in operation in 1949. The basic plutonium finishing operation at PFP consisted of several standard steps. These included purification or wet chemistry, hydrofluorination or dry chemistry, reduction, casting, machining, coating, and final inspection. Even as the first full plutonium finishing line was starting up in the PFP building, design was underway for another line that would operate remotely in a mechanized manner, thus providing an extra airspace and contamination barrier between operators and the plutonium in the glove boxes. Known as the Remote Mechanical A line because it was the first of its kind at Hanford, the new process was completed and commenced hot operations at PFP in 1952. At PFP, many projects were undertaken in an effort to accommodate the increased reactor throughput and the vast production increases generated when the Purex plant came online. In September 1956, Purex demonstrated a sustained spent fuel processing rate of 16 metric tons per day and an online efficiency of 99%. Beginning in 1963, the Purex plant was modified to allow for the processing of in-reactor fuel. Since in-reactor fuel elements were much larger than the single-pass reactor's fuel and were clad in zircaloy metal, they were more difficult to dissolve. Once Purex began the separation of this fuel in 1967, the entire context of production rates and numbers changed for Purex. The processing rate fell to about 2,000 metric tons per year for in-reactor fuel, from 5,000 to 7,000 metric tons per year, which had been normal for the plant during the early 1960s, when single-pass reactor fuel had comprised the entire portion of the feed material. In 1972, the Purex plant entered a temporary shutdown period planned for 18 months to allow for the accumulation of in-reactor fuel. However, the shutdown continued for 11 years. During this time, significant changes in waste disposal and environmental policy were implemented at the Hanford site. As part of the new policy, new waste would only be stored in double-shell tanks, and the Purex restart was further delayed as double-shell tank farm facilities were constructed. In 1983, the Purex plant reopened with an operating limit allowing it to process 8 metric tons per day. In 1988, Purex operations were again suspended, and the facility was subsequently placed on standby status by the Department of Energy, and a final closure order was issued in December 1992. However, even today, most of the world's military and civilian spent nuclear fuel processing is based on the Purex process. Although plutonium production ended at Hanford in 1989, and many of the reprocessing facilities and reactors are being readied for dismantlement, Hanford is serving a new and important role in limiting the spread of nuclear arms. Hanford has been opened to the international arms control community as a classroom for nuclear nonproliferation, safeguards, and verification technology. It is also the site of the first U.S. weapons-grade plutonium to be placed under international safeguards. The technical expertise at Hanford is currently being applied to nuclear nonproliferation by assisting the Russian Federation in converting its last production reactors to power rather than weapons-grade plutonium producers. The world's first production of nuclear weapons plutonium began at Hanford in 1944. It's fitting that Hanford, over 50 years later, is now engaged in facilitating the international cutoff of nuclear weapons material production